Hi everybody, gonna start with a little bit of fun. Nothing like some fun, is there? Tonight's recordings are sponsored by Ozark Trial, so bring your coffee. And this is something you won't find in any of the textbooks, especially for you. If we start off with the engineer's bending equations, I can remember what they are. So far, in terms of stress level 1, we've just really used this term here and maybe got the factorial equation, looking at really the stress. So that's going to be I. So now what we're doing with this particular section is we're looking at more deformation, and we're wondering how we can deal with this term here, so this radius of curvature. So recall when I put a load on a beam, I'm going to apply my load, and I'm going to assume that this is going to be able to create a radius of curvature which this term here will fit through. Okay, so apply this load and we end up with, I don't know, something like this. Okay, so it looks a bit like a circle. So you can then say, I can fit a circle through that curve there, and that's my radius of curvature. And now there's the thing that Arnold mentioned in his lecture, where you can then do a partial second order differentiation, where we're going to define y to be how far this so this is going to be my original y, if you like, so that's my starting point. Be careful whether y is pointing up or down. I think it's going to be pointing upwards. And then I'm going to be looking at how far this y has gone from that point there and moved downwards. Okay. And do a lot of complicated maths, and you get the radius of curvature will fit through this partial second order differential of y by x. So we're finding a second order differential here, and then we multiply it by 1 plus a first order differential, which I need to square, and that's to the power -3/2. Right, so this is Ian Barton's proof of what we're going to do, and of course what you then do is, so we use this bit and this bit of the equation. So we've got m over I equals E over R, so that's going to be my m as I go along the beam, and I know the m varies along the beam, you know. So for example, this shear graph that we'd get, first of all, depends on what convention we're using, but we'll go for the UE convention. So we're going to go up, down, back up again. So that's my shear force graph. And then if I do my bending moment graph, that's going to go up and up. So it's going to be positive. That's my bending moment graph. And we're using the UE convention. Positive m means that we get sagging. So it does almost like a bit of kind of like the reflection of what we're getting here to here. So that's what the m is, and the m is obviously varying with x as we're going from one end of the beam to the other end of the beam. This term, so we assume that our beam is going to be made out of consistent material. Not necessarily, we could actually vary it, but we assume that the Young's modulus stays the same, and we assume that the cross section and therefore the second moment of area stays the same. So these two are going to be constants, and then that leaves us with 1 over r equals, what will that be, m e I. So that's all just a constant. This m is a function of x, as I go from there to there. And this is a little bit of maths which Arnold quoted from the book, and we will not be integrating this because we would take quite a while trying to do these integrations. So we're going to simplify this term down, say this tends to be quite small, so we can simplify this down to 1 over r approximately equals the second order differential of the deformation as I go along the beam, differentiated with respect to x twice. So that's how my y is varying. So this is my actual y deformation. Okay, so I've got a y, and y is varying along the beam. We've got how m is varying along the beam here, and we normally call this q, how the shear force is varying along the beam. So the question is, can I come up with a simple hand wavy explanation for why 1 over radius of curvature is the second order differential? So this is my starting point. I'm going to assume that I'm somewhere along the beam and that I can fit a radius of curvature like this. So we're going to go r. So we're imagining that the beam is curving like that. Right, so I then say, well, let's make this into a bit of a triangle there, and I think I'm going to make that a right angled triangle like that. I've obviously swept through a certain angle there, theta. This length here, well, imagine this tends to become very small, and you should know that. So we are now going to sort of like compare this with what it's really doing. What it's really doing, it's doing like that. So it's doing a path. So the s is the distance of a path. Provided theta is in radians, I can then say that distance is given by the radius times theta. So we've got that distance from there to there. Make my theta very small, so assume that it's not deflecting very much, and then you can say that this distance here is going to be approximately r theta. So that will be 1 point there. Now the next thing is to look at this in terms of relationship of us going down the beam here. So y is getting deflected slightly upwards in this particular case, so we're doing probably some sort of sagging case, and we've moved a certain distance x down the beam. I'm going to draw another right angled triangle there. Okay, well, let's put this triangle onto here, and I can see, well, if this is a right angled triangle, and if I make this one, well, that makes this theta here. So we've got theta here. Yeah, so we're doing another right angled triangle there from that point to that point. Okay, so that then gives me that tan theta equals, well, these are changes in y and changes in x, obviously. So that's going to be delta y over delta x. I use the small angle theorem. Check it out in your calculator if you haven't. It's great fun. So the small angle theorem says that, again, provided we're working in radians, sine theta approximately equals tan theta approximately equals theta. Set your calculator to radians if you don't believe me, and try it for yourself. Well, in this case we're using tan theta. Try putting tan theta equals 0.1 into your calculator, and then tan equals 0.01. then tan equals 0.001, and so on and so on. And you'll find that the result that you get, provided you radians, starts matching closer and closer to that original number that you put in. So that's called the small angle theorem. So we're now going to drop this down to theta equals delta y over delta x. Okay, so that'll be part of my proof. Now the next part of my proof is to say, well, I've moved from here to here. I'm going to take that to be differential. So we're going to say that we've moved s delta, we've moved s by a little bit. The radius of curvature is almost like a kind of constant so as we swing through our path, and we've moved by delta theta. Right, so let's rearrange this so that we have now 1 over r equals delta theta over delta s. Okay, where am I going? I don't know. Next stage is to say, but theta is delta y over delta x. Let's substitute that in there. So I then have that we have a delta. You can see where that sort of complicated little first order differential squared and business is coming in. It's coming in with this pretending delta s and delta x are virtually the same thing. Is going to be delta y over delta x. Go back to my graph here, and if it's only going to be a very small deflection, I can therefore say that delta s is going to be the same as delta x. So we've got then delta x over differentiated by the partial differential of delta y by delta x, and that then gives me what I'm looking for. Okay, so here is a very dodgy statement, and also I suppose you could say that this diagram is a bit dodgy, but provided y is very small, the s and the x are going to be very similar, and also that diagram becomes valid. Okay, so well, we knew it was approximation anyway, so that then gives us that 1 over r can be found by the second order differential of the displacement, which we're using the y variable. Most textbooks use a v or a Greek looking sort of mu symbol, I think it is. So but we're going to use y for our deflection. So don't get confused with this y and the y that you're going to see back in the engineer's bending equation. So it's not this y here that we're looking at. Okay, but it's more convenient to work in delta y, delta x, and we know that y is kind of like how far we're deflecting. Okay, so that's why a lot of textbooks don't like to use y there. Right, so that was an added bonus.